Hi guys, hope all of us are doing great. My name is Ernest. Today we are going to look at this specific topic under the concept of atomic structure. But basically this is also going to assist us in understanding various topics that we're going to look into in quantum mechanics. And that is basically the concept of a quantization of energy, which of course we're going to do in a figurative way in this introductory part. Now, this is going to be based upon the Niels Bohr's interpretation of an atom, whereby he suggested on the concept of electron nucleus, a system of an atom, whereby if I can figuratively give this, we can be able to just illustrate an atom that consists of a nucleus that has neutrons and protons. And therefore, at this specific point, there is an electron that is revolving around this specific atom. And in an essence, for us today, we're going to look at this particular case for hydrogen, which consists of this specific electron. Now, in a sense, Bohr's argument was that this hydrogen model was having an angular momentum that consisted of a stationary state in an integral multiples of h over 2 pi. And we're going to see that this number is going to give us a clue on how we can be able to describe the concept of quantization insofar as this Bohr's model is concerned. And therefore we can see that by trying to figure out an atom in this particular aspect, then therefore we're going to perceive an electron as a standing wave in an orbit around a proton, and therefore this particular wave is going to have what we refer to. We had looked at the anatomy of a wave and we had said that that particular junction between the x-axis and the part of a wave is referred to as a node. And therefore we're going to see that in this standing wave that is being described by this Bohr's model, we are going to have what we call nodes, and they're going to be an integral multiples of wavelengths. We are saying that the wave consists of various parts, and one of them was a wavelength. So I'm going to give you just a mathematical interpretation of this particular aspect so that we can be able to understand what we are talking about. So in a sense, we had said that from this particular symbol that we had given, which was lambda, this is lambda. We said lambda refers to the wavelength, and this was described for the subatomic particles, which we had said can as well act as which have a characteristic of a wave particle duality. Therefore, they can be described as a wave. Now, this particle, like an electron, can be described as a wave. Therefore, it's going to have a wavelength, which was described given using this lambda as h over p, where p represents the momentum. So therefore, in this case, we can be able to describe this electron that is being said as a standing wave in this particular case using this particular wavelength, whereby we are going to have an aspect of this distance that is being covered, which basically is the circumference, and we can have this circumference as a multiple number over this particular range of wavelengths. Now I'm going to do this one using just a product diagram of or a rather different version of this particular diagram, which is going to be illustrated as. Now if we try to visualize this, we're going to describe this one using L. Of course, I had talked about different quantum numbers that we're going to give for this particular electron that is revolving or having a wave like characteristic around the protons. So this is around a nucleus in that particular case. So we have the protons and the neutrons in this specific nucleus, and then we have an electron that is behaving as a wave in this particular case. Now for us to justify this, we are going to see that this angular momentum number can be described as the product over this particular distance and then the momentum. And therefore this is going to give us a case whereby we're going to see that this is going to be an integer, which is a multiple of that particular case, which is going to give us nh. And in this case, in trying to figure out how this one can be represented, suppose we have this particular wave that is moving from this specific point to this one, that will form a full cycle of a wave, and then therefore we're going to describe this one as a wavelength, and therefore we're going to see that a specific number of wavelengths are going to form this specific circumference that I've drawn on the board. Therefore, this is going to give us a description of what we have given on our left side. So suppose I'm just to repeat what I'd given before. So I can say that if I'm to describe this circumference using the normal formula that we use, this is for 2 pi r, which is the circumference of this particular case with regard to this wavelength, then I'm going to have this one as a particular number of wavelength times n, and then this is going to give me the circumference for this. So in this case, this implies therefore that I'm going to obtain this particular case for n, and the description for lambda is going to be h over pi. So therefore I'm going to have n, and the substitution for that is going to be h over this is p, of course, not momentum. This p naught of pi, of course. So it's a multiple of h over pi, which are going to be this particular wavelengths that I'm giving in this case. But of course, we're going to expand this one more, so we're going to see other formula which are going to assist. But of essence for us is for me to try and illustrate the relationship between these particular multiples over this particular wavelength that I've given on the board, which basically is an aspect of h over 2 pi, as I've illustrated on that part of the board. So therefore, of essence for us to try and note from this particular point, then therefore we're going to see that the relationship between angular momentum L, which is basically being described as a multiple, an integral multiple of h over 2 pi, can be shown to have a relationship with this particular case, whereby we're going to see that basically this implies that this standing wave will have nodes and be unintegral multiples of wavelengths, which I've given in terms of this specific description. I hope that one is understood. So having mentioned that, we're going to look at Bohr's atomic model and the various spectral lines that we are going to encounter in trying to describe this hydrogen atom. So earlier on we had mentioned about the emission spectrum of various atoms that we're going to, of course, encounter in this discussion. So I've mentioned that the atomic spectrum of atoms are very specific, and therefore the atomic spectrum of hydrogen is going to be shown to consist of a series of lines which occur in the visible region of the spectrum, as I had mentioned. So therefore, the spectrum, the atomic spectrum of hydrogen atom is going to occur in this visible region of the electromagnetic spectrum. And these lines are going to be formed by emissions of electrons falling from higher energy levels to the subsequent lower energy levels. And as I had given in this specific general illustration for an excited state of an atom, and then whenever this atom loses the energy, it falls into the lower energy levels. So therefore, in this case, we're going to encounter various lines which are going to be depicted using this particular case for hydrogen. And these lines are going to be formed, as I said, from atoms, of course, losing, or rather, going to be formed by electrons which are excited and falling to the lower energy levels as such. And we're going to see that these energy levels are going to be given numbers, which I'm going to use illustrate using the specific illustration in this particular case. So suppose I had this particular illustration. Now this has a series of emission lines which I've drawn on the board, and they have different names and we're going to, of course, try to look at these various parts. Now this one illustrates the excited state of electron falling into lower energy levels, and we have various names for each specific energy level. Now for the first one, it's going to be given as N1, Now, whenever we are going to see that this series of lines formed by a transition to N1 are found in the ultraviolet region of the spectrum, the UV region of the spectrum, it's a transition of course, to N1, and they are referred to as the Lyman series, and this forms the first series of these specific lines. Now, the subsequent transitions shows the transition from a higher energy level to the now for this one, this is a transition to N1, and the second one, this is a transition to N2, is given the name Balmer series. The transition to N3, this is given, or rather, let me just give it as this: N is equals 3, N is equals 2. It's known as the burst change series, and the transition to N is equals 4 is referred to as the brackets series. And lastly, the transition to N is equals 5 is referred to as the P-fund series. Now, these series are going to, of course, assist us to try and figure out how we can be able to describe the various energies of these particular lines. And in our case here, we're going to see that, of course, these spectral lines are going to be described using a particular formula that we're going to learn later. Now, of essence for us is to try and see that basically, as we had advanced from the concept of electromagnetic radiation spectrum and energy, these are specific lines that are going to be encountered whenever we are trying to describe this Bohr's model of the hydrogen atom. Later, we are going to see some of the shortcomings of this particular case for the Bohr's model, and try to see which are some of the ways of the alternative description or other arguments that have been advanced in order to explain the particular characteristics that we're going to encounter for this. So the Rydberg's equation is going to assist us to try and describe the various transitions that we have learned. And in this case, of course, just leave it there for another discussion of how we can be able to quantify the transition of these energies of the various series that we have looked into. So I hope the Bohr's model of the hydrogen atom has been well understood using this figurative description. And let's catch up in our next video, where we're going to look at John Balmer's description of this particular transition that we have talked about. So that is it for today, guys. Bye. Let's meet in our next discussion.